Okay, welcome everybody to a new Astronomy on Tap Leiden online edition. We're very excited to be back here today. And we have a very interesting program for you. We have two speakers, Alessandro Sonnenfeld and Kirsty Butler, and they're going to be speaking about gravitational lensing. So for those of you who don't know Astronomy on Tap yet, this initiative started in New York City in 2013. And it quickly spread throughout the whole world. We have 40 locations right now. And Astronomy on Tap Leiden started in March 2017. And we have an event every last Monday of every month. Usually we do it in the Burgt, but now with Corona, we have our online version. So tonight, we're streaming online via YouTube. We have Lamim as a questions moderator. We have Marta hosting the games. Then we have Andres for the technical support and Alessandro and Kirsty as speakers. You can leave your questions for the speakers in the live chat on YouTube. So please just do that during the talk. And then after the talk, we'll have the moderator to ask them at the end. And please let us know in the chat if you're watching. Interact with us on social media, on Facebook, for instance. So here we see two images from last events that people posted. So we really appreciate that. And go sit and have a nice beer. So here are all the social media channels where you can interact with us. So please do not hesitate to contact us in any way. And as usual, we start with a little astronomy news of the month. So here you see this beautiful image of the X-ray sky. And this image was taken only about a week ago by the X-ray satellite eRosita. And eRosita left Earth about a year ago. And it actually took the satellite about half a year to make this X-ray image. And this is an all-sky image you see here. And it's actually really special because it's the deepest all-sky X-ray map made so far. So here in the middle, in the blue, you actually see our own Milky Way. And above and below in yellow, you see the hot, energetic gas from the Milky Way. But then if you also look below and above the plane of the Milky Way, you see all these tiny white dots. And those are actually mostly like very far away luminous galaxies. And this mission actually roughly doubles the number of known X-ray sources. So this new map and this new data is going to give us a whole lot of new, interesting and exciting science. So for tonight's program, we're going to start off with a talk from Alessandro Sonnenfeld. He's going to be talking about space warps, which is a crowdsourced search for gravitational lenses. Then we're going to have a quiz and a short break. And then Kirsty will be talking about gravitational lensing and detecting the silent but deadly. So if you want to know what that's all about, stay tuned. Then we'll have the quiz answers and the winners, and then we'll wrap up the night. So first, I would like to introduce to you Alessandro Sonnenfeld. Alessandro is a Marie Curie Fellow at the Leiden Observatory. And here he studies early type galaxies, and he studies those using gravitational lensing. And he was born and raised in Italy, where he studied at the University of Pisa. And afterwards, he moved to the US, where he did his PhD at the University of California in Santa Barbara. And after this, he also moved to Japan, where he worked at the Kavli Institute for Physics, Mathematics of the Universe. And here he also played the trombone in the orchestra of the Kavli Institute. So that's what you see here in the image, a very brightly colored, happy trombone. So yeah, I give the floor to you, Alessandro. Thank you very much for being here.
Thank you, Anik. Let me share my presentation. Right, so yeah, so the title of my talk is Space Warps. Space Warps is the name of a citizen science project that's aimed at discovering new gravitational lenses. So first of all, what is a citizen science project? Well, citizen science is when scientists asked for help to the community, to volunteers, to carry out a task that would otherwise be very difficult to complete just by the scientists. And in this case, the task was classifying a large number of images to look for gravitational lenses. So what I'm gonna do here is I'll try to explain what a gravitational lens is, and then I'll tell you more about this citizen science project. So first of all, in this slide, in the background, you're seeing a series of images, and all of these are gravitational lenses. So a gravitational lens at its minimum consists of two objects. One massive object in the center that we call the lens, and in this case, the yellow circular thing in the center, that is the lens. And then it's surrounded by an arc. In this case, they're all blue arcs. What these are actually galaxies that happen to be behind the yellow one. So why do they look like arcs? Well, the basic phenomenon here is that of light deflection by gravity. So in this diagram here, you have to imagine that we're at the left of the image where it says observer. In front of us, there's a lens galaxy, a massive object, a galaxy. And behind it, there's another galaxy, the spiral one here. And in normal circumstances, if there was no galaxy in front of it, light would travel straight from the source directly to the observer. But due to the gravitational field of the galaxy in the middle, light rays get bent. So gravity deflects light, and as a result, we receive light rays that go through this interesting path. So they start from the source galaxy, and then they go up, and then they deviate and come at us from different angles. So what happens is that we see light arriving from a different direction compared to where the galaxy actually is. Not just that, but if the alignment between the lens and the source is good enough, you can actually see more than one image of the source. And that's what these elongated images at the top and the bottom of the screen are. This is one of the things that is much easier to explain in person, but I hope you can get the idea. One thing I want you to know is that the separation between the observed images, or in other words, the angle between these two light rays that get to the observer, that angle is proportional to the mass of the lens. So to the mass of the more massive the galaxy in the middle is, the more the images get separated. This is very important because we can use this to actually measure the mass of the galaxy. And that's quite useful because there's very few ways of measuring the masses of galaxies. And this is among the most reliable, if not the most reliable. And the physics at the basis of this is the theory of general relativity of Einstein, and this is a tribute to it that you can see in Leiden, actually. And here's a little movie that I've made to illustrate the phenomenon. So this is a simulation. So what I've done here is I've put a lens in the middle and I keep it fixed. And then I'm moving a source behind it. And So what you see is when the source is far away, you only see one image, but as it gets closer, you start, so a new image starts appearing at the opposite side. And then as it gets even closer, as the source is right behind the lens, you actually see a full ring, which we usually call an Einstein ring. So the configuration that you get depends on the alignment between the lens and the source. And another thing I want to point out is that lensing doesn't change the color of the background images, of the background image. Even though in this case it might look like the source is getting a bit more white, especially during the ring phase, that's just a saturation effect. Okay, and here are some images of real lenses on the left. The top left one is my favorite lens, if anything, because it's the first one. I had the privilege of studying it as I was starting my PhD. And if you look carefully, it's quite interesting because it has two sets of arcs. So there's the lens, the yellow thing in the middle, and there's a pair of arcs of the same color. And then there's another set of arcs further out. So what's happening here is that there are two galaxies behind this lens. So there are three galaxies lined up, one after the other. And that's very rare and cool. And for this reason, this lens was dubbed the jackpot lens back in 2007 when it was discovered. You don't always get arcs. So this lens on the top right, here you see four bright dots. And you get that if the light source in the background is very compact. So yeah. And you can also play with your own lens with a wine glass. So that's what this image on the right is about here. I was holding a wine glass and shining light through it, and it turns out the properties, the optical properties of the bottom of the wine glass are not too different from those of a gravitational lens. And so if you play with it, you can produce images that sort of look like arcs that you see in a gravitational lens. So lenses are pretty. I hope you concur on that, but they're also quite useful. As I was mentioning, we can use these to measure the masses of galaxies. We can also use these to look at, so lensing magnifies images. So we can exploit this to look in greater detail at the images of galaxies that would otherwise be too faint. And we'll learn more about this in the next talk. So lenses are useful, but they're very rare because they require an almost perfect alignment between two galaxies. So at the moment, the number of known lenses is around 1,000, which is quite good, but for many purposes, we would like to get more. And this is where citizen science comes in. So the first efforts at lens finding with citizen science was started by the SpaceWorks collaboration, which was led by these three people that I'm showing here. And 2 years ago, I was invited by them to launch a new campaign based on using data from the Subaru telescope, which is a Japanese telescope. So we did it. We uploaded 300,000 images of galaxies on our website, spaceworks.org. And that was actually hosted on Zooniverse. Zooniverse is is a very cool project that hosts all sorts of citizen science projects. So if you think you might be interested, I would highly suggest you check it out. There's all sorts of projects you can be involved in. Some are more fun than others, but SpaceWorks was a fun one, I think. So we started in April 2018. The project lasted a few months. Now it's over. The website is still up. It looks like this. Unfortunately, it's not active in the sense that you can't actually, there's no data for you to play with at this stage. But you can at least look at the information material. So if you click on Get Started, you'll be shown a brief tutorial. And then when the experiment was going on, this is what you get. So we show you images of a galaxy. So in this case, the 4 panels are just 4 images of the same object. The ones on the right here, we try to remove the light from the lens to make it easier to spot features. So we show you an image, and then we ask you to click on it if you think it's a lens, or just move on if you think it's not a lens. It sounds hard, and it is. At the beginning, at least, it takes a bit of practice. But the way we teach volunteers to recognize lenses is through training images. So especially at the beginning, every few image that pops up is an image of either a lens or something that we know is not a lens. So is a training image that we prepared. And after you submit your classification, you get a feedback message. If you got it right, we say congratulations. If not, we'll say, well, maybe you can try again later. And it works. And here are some examples of training images. The ones on the left are lenses. They're simulated ones. The ones on the right are non-lenses. And you know, at first it's quite hard to tell the difference, but it doesn't take long to learn. The trick is, in this case, that the non-lenses are spiral galaxies, and they tend to be more fuzzy, more irregular. The lenses tend to be more smooth. So after a few images, everyone can actually differentiate between the two. So yeah, the campaign was successful. We gathered 2.5 million classifications in just over 2 months. We had nearly 6,000 volunteers participating. And in the end, they gave us a sample of 1,600 candidates of things that they thought were lenses. Then we got together, so a team of experts in lensing. We further refined the sample. We threw away roughly half of these that we were confident were not lenses, and we were left with 700 or so possible lenses, which is a huge achievement. It would have been very hard to get to the same number without the help from the volunteers. So what I'm showing here, and this is my last slide, is a selection of my favorite lenses, and I picked these. So the 2 columns on the left, these are specifically selected to have very small sources. So these are all of the point-like kind, and they're quite interesting because they could be quasars. So the source could be a supermassive black hole that is accreting gas, or not. We don't know. And on the right, I'm showing disk disk galaxy lenses. And these are interesting because they're also quite rare. And so in one campaign, we were able to almost double the number of known disk lenses. So I hope you like these images, and I'm happy to take questions.
Thank you, Alessandro. That was a very interesting talk. And we have one question, actually a few questions from the audience. So the first question is, why are the two images mirrored? I think it's about the first image that you showed about the lenses.
Yeah.
Yep.
Well, yeah. You can maybe see it if you start tracing light rays from different parts of the galaxy. Well, it's not that obvious, but it's just a geometrical effect that if you go one way, if you go above the lens, so there's the image that is that happens to be on the same side of the source with respect to the optical axis, maintains the orientation. So the light rays keep the same ordering, but if you go the other way, then the light rays from different parts of the galaxy starts crossing each other, and you end up with the flip image. But there's no, it's not something I can, it's particularly intuitive that I can prove right now. But that's a good question.
Thank you. And the next question is, so what have you learned with these 700 more lenses?
One thing I've learned is that in some cases, volunteers are better than experts in recognizing lenses. We had some of these volunteers were really good. The thing is, they found lenses that are very faint, and many of the expert teams discarded these as non-lenses. And I personally stand with the volunteers on that. I think many of these turned out to be lenses. So maybe scientifically it's not a great discovery, but it's something to keep in mind, because it matters when an important piece of information is how many lenses total are there, and if we have to be very careful about how to quantify how good we are at well, what is the fraction of lenses that we're missing. So we have to think carefully about the actual definition of a lens. But so this is in a way is just a starting point. Once with these 700 lenses, what we're going to do is we're going to then target many of these with spectroscopy. So there's a new spectroscopic survey that is going to be done with the Subaru telescope, and so we hope to get more information out of these.
Okay, great. Thank you. I think we have time for one more question. I'll just do, can you extrapolate the distance between source and lens galaxy from the image?
Well, usually, well, no. The short answer is no, because the image that you get, you can get the same image either by moving the source away. So let's play like this. If you make the lens galaxy more massive, you can get the same image if you move the source galaxy closer. So there's it's hard to distinguish whether it's the lens that's more massive or if it's the source that's further away. So, but what we do is usually the other way around. We measure the distance of the source, and then we use information to measure the mass of the lens.
Great. Thank you, Alessandro, and thank you all for the questions. And now it's time to move on to the games. Marta?
Yeah, thank you very much. Now let's start the games. Okay, welcome everyone to the games. I hope you enjoyed the Alessandro's talk. Today we have prepared 2 games for you. Here on screen you have the link to the Google form. And also Anik will have just posted it online on the box chat on the right. You can click on it. The first game we have is this a gravitational lens, yes or no? So we'll show you images and you just have to decide if you think this is a gravitational lens or not. So the first one. Number 2. Number 3. Four. We will go through all these images again at the end of the games. So if you don't have time to decide for any of them, don't worry. Number 5. Six. Seven. Eight. 9.
And the final one. Great. I hope you've put all the knowledge that all the things Alessandro just taught you to good use. And now we move on to the second game of the night, which is a gravitational lensing trivia. Question number 1, how many gravitational lenses have been detected so far? A, 10, B, 100, C, 1,000, or D, 100,000? Number 2, what property of the image of a galaxy is not changed by gravitational lensing? A, its shape, B, its total brightness, C, its color, or D, all of the above? Question number 3, what discovery has been made by gravitational lensing observations? A, most stars in the Milky Way have at least one orbiting planet. B, confirmation that the Earth is round. Or C, the expansion of the universe is accelerating. Number 4, what kind of lens is capable of producing images with the largest angular separation in the sky? A, a stellar black hole, B, a supermassive black hole, C, a galaxy, or D, a cluster of galaxies? Question number 5. When was the first multiple imaged gravitational lens discovered? 1916, 1927, 1979, or 1999? What object acted as the lens in the first ever detection of bending of light by gravity? A, the Andromeda Galaxy, B, the Sun, or C, the supermassive black hole in the center of the Milky Way? Question number 7. In November 2014, astronomers found 4 images of a single lens supernova. They predicted that a 5th image of it would become visible later, and it indeed appeared in December 2015 at the predicted location. What causes such a time delay? A, the light takes a different path with different distances. B, the speed of light was lower on a different path. Or C, some object originally obscured the 5th image. Number 8, gravitational lensing has the strongest effect on A, X-rays, B, visible light, C, gravitational waves, or D, on all of the above equally. Okay, so that was the end of our second game, and now on for the tiebreaker question. How many years did it take for light to travel to Earth from the most distant gravitational lens ever found? We will now go on to a break of a few minutes. I will cycle through all the questions again in case you missed any of them or you need more time to think about them. And then at the end of the break, we will close the form and we will announce the winner and the answers to the questions at the end of the second talk. Okay, so that's it for the games. I hope you enjoyed it. We will be back in a few minutes now, and remember to submit your answers by the end of the break.
Okay, we're gonna start again with the second talk of the night. So I'm happy to present to you Kirsty Butler. And Kirsty is a PhD student at the Leiden Observatory. And she's a self-proclaimed gastronomer because her research focuses on galaxy outflows. Before she came to Leiden, she did her undergraduate at the University of Western Australia in Perth, where she majored in physics and astronomy. And then she did her master's in astronomy and astrophysics at the International Center for Radio Astronomy Research. And here she focused on measuring the angular momentum of local dwarf galaxies. And Kirsty calls her greatest achievement in life what you can see here on this slide. This is the Belmont Primary School Book Week costume competition. And this she won 3 years in a row. And I think we can all agree on you winning in this competition because your costumes look truly amazing. So thanks a lot for being here, and go ahead.
Thank you, Anik. I'm obviously living in the past. So good evening, everyone, in Europe at least. Good morning, anyone who's watching from Australia. I know there's a few of you. So I'll just start my presentation. So yeah, I'm Kirsty Butler and I'm a PhD candidate at the Leiden Observatory. And I do indeed study gravitational lenses and outflows. So I think I might have brought you all here on a bit of a false pretense, especially because gravitational lenses is the theme tonight and is in my talk. But as you'll see, it's not necessarily the thing that I care the most about here. And the more mysterious second half of my title, Detecting the Silent but Deadly, is really the focus here. So we'll get to that point, but I'll tell you why. So Alessandro talked to you a little bit, first of all, about this gravitational lensing and how we can get beautiful arcs in our skies where galaxies behind other galaxies get magnified and stretched into these cool things. And to be honest, I don't know, universe, like it's cool. It's a bit of a magic trick. But like Alessandro said, Einstein worked it out. And once you work out a magic trick, things like this just don't seem as cool anymore. The mystery has gone. Obviously the universe was happy this day and it decided it wanted to smile at us. But I don't know, guys. I think they're cool, but most of all, what they're good for is how we can use them in our science to look at other things. How can we use these to learn more about the physics of the universe? And that's what I'm going to talk to you about. And I want to move on to a subject that I really enjoy, something that I'm super passionate about, and that's galaxy formation and evolution. So you might know some galaxies. We live in one called the Milky Way. We have a few close by friends called Andromeda, or the large and small Magellanic Clouds. These are all galaxies. But like this galaxy you see before us, it's beautiful, it's big spiral galaxies. These are all really close galaxies. And they do not start out like this. In the early universe, they're a complete mess. And actually, this is a nice way, I think, to think about them. They're not just objects, but they're forming and they're evolving through time. They're like living beings, and they go through a lot. Galaxies have seen some stuff. And so we as astronomers, I'm an observational astronomer, so I take lots of images. We unfortunately can't video our galaxies growing up. Fortunately, there are people in astronomy who simulate the universe in computers. So whilst we can't video our galaxies, we can look at this evolution in a computer. And I'm going to show you a video now. It's not the real universe, but it is the universe, and it sort of demonstrates some of the stuff that galaxies go through. So like I said, in the early universe, all we started off with was a bunch of dark matter and a bunch of hot gas, and somehow out of this, galaxies form. So the first thing to form are dark matter halos. And then after a while, some of the hot gas in the universe starts piling into these dark matter halos. So you see this here. We have a galaxy forming in the center here, and all of this gas pouring in from the sides and and making this galaxy in the center. So you can see down the bottom here, we have the gas in this square, and then we have the stars in this square. Because as gas pours into these galaxies, it condenses and it gets cold. You might form some dust, but eventually it'll start forming stars. Some of these stars will have winds. Some of these stars will go supernova in huge explosions. Some of them will turn even into black holes, and black holes themselves blow a lot of gas around. They have a lot of energy. Now I'll just stop it here for a second. Whoop. No, I won't. I'll play it again. So as all of this is happening, all of this energy is being turned into stars. These stars have these winds, these black holes have these winds, and some of this energy, and particularly during sort of the teenage years of galaxy evolution, a lot of this energy goes back into the gas in the disk. And what happens when all of this energy goes back, it starts pushing the gas in the galaxy out of the galaxy in these outflows. Now, you may not have noticed this the first time we watched it. It's pretty easy to see the gas flowing in and the gas in the galaxy spiraling around. But if you look closely, there's also these big shells of gas expanding out from the galaxy. And this actually has a very big effect on the evolution of the galaxy itself. Without any of these outflows, without any of these feedback, we actually wouldn't get any of the disk galaxies that we see in the local universe. Star formation would occur rapidly and die down rapidly as well in the universe, and everything by now would actually have completely died. So these outflows are incredibly important in the evolution of galaxies as we know them. But they are difficult to see. Even in simulations, it's difficult to see. But they're important, and we know they're important, so we have to go out and we have to look at them. Now, I told you already that we can't take videos of the universe. So if we actually really want to go out and observe reality, we can't take a video, but what we can do is we can look through the universe at galaxies in the distance. Now, what this does for us, and this is a picture of the whole universe. Over here, we have the Big Bang. Over here is a telescope at today. And so the further you look back, the further away we look in the universe, actually what we're seeing is further back in time in the universe, because any light emitted here has had to travel all the way to us, and that takes billions of years. And so what happens when we look at this light that has had to travel for billions of years is we get a snapshot of that galaxy billions of years ago, so when it was only young. And people have gone through this. And like I said before, you know, we want to look at the outflows. We want to know the impact of outflows on the evolution. And it's, you know, you have to look at galaxies where we think the biggest impact of these outflows are. And like I said, these outflows are driven by star formation or black hole activity. So people have actually gone along this line of the universe and they've measured these properties of galaxies. So I'm going to show you a plot now. And this is the star formation rate density of the universe at each particular time. So this is today, 0 here, and we have the star formation rate density. So how many stars are being formed at a certain time in a certain area in the universe, all the way to almost the beginning of the universe. So over here at the beginning of the universe, star formation rate density is pretty low. We've only got little baby galaxies that have a lot of gas, but they haven't started forming too many stars out of it. And this really ramps up as galaxies come into their sort of angsty teenage stage. So, you know, Mama Universe is giving them lots of gas, they're guzzling it in, they're turning it into stars, and they have so much power and they've got all this mass and they don't know what to do with it, and it starts blowing out. And, you know, well, life is tough, but these are the guys that we want to go after, because this is where outflows are at a maximum, where star formation rate, density, and where the black hole activity in galaxies is at a maximum. Eventually they kind of calm down and they've drunk all their gas. They've drunk all their gas, they've made all their stars, they've done all their outflowing, and they turn into sort of red, dead elliptical galaxies. So these galaxies, this evolution that I've sort of laid out here is what we call, these are dusty star-forming galaxies in their teenage years. They're sort of the early bloomers of galaxy formation. They form really young, they form really fast, and they die pretty young too. All right. So we know where to look. We know why we're looking for outflows. So you've probably worked out now what the second part of my title is. So we've got gravitational lensing, and we're still getting to that, but the silent but deadly. Now, it's something to remember. In space, no one can hear you fart. And that's why it's silent but deadly, because these things are rippers and they rip their galaxies apart. And this is why the galaxy looks a little embarrassed. And I'm a bit of a creep, to be honest, because I'm going after their farts. But as we saw in the simulation before, these things are not easy to find. I don't know if you've ever tried to find a fart, but they're very weak. And compared to their galaxies, they're very faint. And to find these farts in space, we need the best equipment possible. So this is a telescope that I use in my research. It's called the Atacama Large Millimeter Submillimeter Array. It's a big interferometer. So you got these dishes. It's a big interferometer in the Atacama Desert in Chile. And we use this because we can see sort of neutral molecular gas at these high redshifts, these very distant galaxies. And we need this because we need the biggest telescope to capture the most light that we can from these galaxies. But even with telescopes such as ALMA, it's incredibly hard to see these outflows at really large distances in galaxies that are actually quite compact at this age. And so this is where we need gravitational lensing. So I'm pulling out my utility belt. I need another tool to work with here. Big telescopes aren't enough. And I'm going to lay out just how much gravitational lensing helps us in studies like this. So this is a lens that I look at. And this has a rough magnification on the order of about 10. So we use mu to denote magnification. Magnification, remember, it means that these things look stretched. They've been stretched spatially, but we're also getting enough flux. So with a magnification of 10, which is, not unnormal for a strong lens, our telescope is able to collect 10 times the amount of flux that it would otherwise. Spatial resolution is improved by the square root of 10. And with these things combined, the consequence of this magnification with an instrument such as ALMA, what this gives us is a 100 times improvement in our exposure time. So a lens like this, to detect an outflow, it would take us about an hour with ALMA. Without gravitational magnification, this would take us 100 hours. And now ALMA is one of the most oversubscribed telescopes that we have. Everyone wants to use it. It's the biggest, baddest thing out. And something like 100 hours for one galaxy is huge. They have 5 large programs a year that they spread out across the world, only 5, and they're 50 hours each. So if I wanted to look at 5 galaxies that took 100 hours each, then I'd be looking at all of the large programs for ALMA for an entire year. No one else would get it, except other people would get it because I would not get five large programs to look at 5 gravitational lenses. So instead of 500 hours, we can get these, for example, 5 lenses for just 5 hours without gravitational lensing. And this is really, really, this is why gravitational lensing is in its essence essential for my studies. So here's a bunch of gravitational lenses. I'm actually going to focus on just one for you tonight, this guy. So this is one of those angsty teenage galaxies. It's called a dusty star-forming galaxy. It's sitting at about a redshift of 2, so that's about 11 billion years ago. It's very dusty, it's got a lot of gas, it's got a lot of star formation, right? And I mean, I like this guy. I've spent a lot of times with it, so I think we should all get acquainted. If you want, you can learn its name. It's J085358.9 plus 015537. That's a bit of a mouthful for you. You can actually refer to it with its nickname, which is G09V1.40. Yeah. Astronomers sometimes aren't the most imaginative when they're naming things. I mean, we call our biggest telescopes the Very Large Telescope. So, all right. So let's learn some things about this guy. What you're seeing right now is the dust continuum. So galaxies are made up of 4 major things. We've got the dark matter. We have the gas that pours into the dark matter and starts forming the galaxy. As the gas cools, it forms some dust, and this is what we're seeing here. And some of that gas and that dust condenses so much that it forms stars. And what do the stars do? They cause outflows because they put energy back into the ISM. All right, so this is the dust, but I'll show you some more images. So this is the same galaxy in 4 different components. So on the left here, I've already introduced, is the continuum, the dust continuum. So this is showing the dust in the galaxy, in sort of the galaxy disk. But we can also look at the gas in this galaxy using a CO line. So this traces molecular gas, and this is also in the disk of the galaxy. We have made a choice to try and detect an outflow using OH+. So this is another molecular line that traces neutral gas. And this is our outflow trace. So this is what we have chosen to trace our outflow. And then we also have some Keck data. So this is not taken with ALMA, but this is our stars on the far right. And I've taken this data from Kalanog. So this is all one galaxy. Perhaps if I had shown you these 4 images separately, you probably would have thought maybe there was 4 different galaxies completely. And the reason these things look different is, well, 1, the dust, the gas, the outflow, and the stars don't necessarily have to line up completely spot on. And so they will look different no matter what, but also because this galaxy, and one of the signs that you can take is this galaxy is sitting right behind its lensing galaxy. So we have these 2 big images here. This is the same galaxy mirrored. We have a galaxy in the middle here, which is causing the gravitational lens. Now, when you know that a galaxy is sitting right behind its lens, when you get this Einstein ring, and we can actually see this Einstein ring, but not all of the galaxy is sitting on the caustic right behind the lens. Some of it is sitting just behind, just to the side. And this is why we get these images, and the CO and the dust are sitting at slightly different spots with respect to the caustic. All right. So this is what the galaxy looks like in different lines. And you're probably thinking now, cool, Kirsty. All right, you've told me this is the galaxy, this is the galaxy, and then this is the outflow. But how do you actually know that it's an outflow and not also in the disk of the galaxy? And that's a fair question. And this is where the beauty of ALMA really comes, because for every single pixel we have in our image, and this is the CO 928 line, we don't just know how much light is in a certain spot on the galaxy, but we know how that light is distributed across frequencies. So we get a spectra for every single one of these pixels. And that's what you see on the right here. So this is the galaxy, but for every pixel, I'm showing you a spectra. Now, what we get from spectra is the velocity distribution. So for a pixel that's tracing a little blob of gas here, if that gas is moving towards us, the light emitted from it kind of gets squished on its way towards us, and it ends up looking more blue. And in a frequency sense, that means that the frequency has increased with respect to what perhaps we would see in a lab. If that gas is actually moving away from us, then the opposite will happen. The light gets stretched and it looks more red and its frequency goes down. And we can see that in each one of these spectra. So not only do we know how much light is in a pixel, but we also know how fast it's moving towards and away from us. Now for each of these pixels, this is the CO928, so this is the molecular gas in the disk. We also have a spectra for the OH+. So this is 1 pixel in my data set, and we have the CO928 here shown in blue. And as you can see, it peaks right, well, not right, but like on the 0 line. So this is sitting right at the systemic velocity of the galaxy. But if we look at the OH+ line, which is in absorption here, it shifted to the left by about 250 kilometers per second. So this is actually tracing gas, and we can see it from the spectra. It's tracing gas that's flowing out of this galaxy by at least 250 kilometers per second. So we indeed do know that this gas is tracing the outflow in the galaxy. So once we do this, we know that our line is tracing the outflow, and we know how much of this substance is in the outflow. We can convert it to sort of a total mass. So we can add up all the light and we can convert this to a mass. And this is where the fun starts, right? Like how we want to know in the end, what impact is this having on our galaxy? So just for a reference, the mass of the gas in the disk of the galaxy is about 2.5 times 10 to the 10 solar masses. That's how much gas is inside the galaxy. If you add up all the light in the outflow, then this comes to a mass of 6.7 times 10 to the 9 solar masses. That's a quarter of the mass of the gas in the galaxy. Now, I don't know, I mean, I've done some big farts in my life, but I have never excreted a quarter of my mass. So this is a lot. I mean, if you're thinking of the evolution of your galaxy, if that's how much that is outflowing, I mean, this is extreme. This is ripping the guts out of this galaxy, and that must have an effect on its evolution. One way we like to compare this to sort of judge, what effect, what impact is this actually having on a galaxy, is to compare to the star formation rate. So this is how fast a galaxy is turning gas inside its disk into stars. And the star formation rate for this galaxy is 770 solar masses per year. So 770, suns per year are being formed in this galaxy. If we take our mass from our outflow and the velocity of our outflow, and we assume sort of a radius, then we estimate the mass outflow rate, so how many solar masses are being pushed out of the galaxy per year. We estimate this to be at about 600 to 1,000, and actually probably almost 2,000 solar masses per year. So this is an extreme evolution for this galaxy. So I want to come back to this. So that is, the sort of the big thing of this galaxy. That's really what we're after in these studies, is finding out the impact. But I think you might be interested in seeing the final part. So that's not the end. With gravitational lensing, we get these funny shapes, but this isn't how the galaxy actually looks. And we're also interested to know the intrinsic properties of our galaxy. What does it actually look like if it wasn't gravitationally lensed? I mean, we're fortunate enough to see it like this because it gives us so much more flux and so much more spatial resolution, but what does it actually look like? So this is all of those components in what we call the image plane, and we can actually trace this light back into what's called the source plane and reconstruct this galaxy and make an image of what it looks like in the source plane. And I'll show you that now. So this is our dust continuum. This is how the dust looks in real life, the intrinsic dust profile. And then our CO98 sort of sits on either side of this dust. Our outflow sort of looks like it's creating a kind of a cone-shaped outflow emerging from this dusty star-forming center. And then we have some stars. Now, stars in these galaxies are mostly obscured behind the dust. So we're not seeing all of the stars here, but we are seeing some. So I wanted to make you guys a little cartoon just to give you a more intuitive feel for this galaxy. Like I said at the beginning, I like to think of these things as living objects. So I'll just move this up. And I took a bit of inspiration from my childhood for this part of the talk, and we're at sort of at the end here. And there was a book in my childhood that was very important to me. And I think it taught me a lot, and it really came back to me in this moment. And that book was, oh no, where is it? I'll have to show you the cover later. This book was, the title was, and it was written by Andy Griffiths, who's an Australian children's author, and it's called Zombie Bums from Uranus. Oh, no, wait, it's still coming. Oh my goodness. Okay, here we go. This is Zombie Bums from Uranus. So this is a kid's book that I read when I was younger. It's very important. It's very scientifically accurate, actually. And I was looking at this book again, and I was looking at my galaxy, and I was thinking, you know what, there's something here. So I took a little bit from the cover and I moved it over, and I was like, yeah, okay, this kind of, there could be something here. Then I moved it around a little bit, and oh my goodness, this galaxy is a giant bum. All right, okay, let's keep going. All right, so we've got this bum. It could be a bum. So this is the molecular gas in the galaxy. It's sort of got this kind of two bun thing going. And then, so we take away the CO98, and then what else do we have? Okay, we have, that's right, yeah, okay, we have the stars. Yeah, we have stars. So if we put the stars over, then what do we get? Okay. Yes, okay, I mean, of course, this is a teenage bum. It's gonna have some pimples, and they're probably gonna be pretty ripe to explode. I mean, there is a lot of power in this bum. Okay, all right, yep, all right, so what next? Okay, yes, that's right, we have the continuum intensity. Now this is tracing the dust in the galaxy, right? So we take that away, so. Okay, yeah, all right, so right between the cheeks, we have this sort of gritty, dusty column, and that also makes sense. I mean, teenagers don't always have the best hygiene. So then we just have one last component, which is our OH plus outflow, and we put that over the top, and yes, we have a fart. We have a giant fart. And now this isn't an AGN, otherwise I could say it's coming right out of the hole in the center, but it's probably not. So it's just the pimples in this case. So we have our G01.4V, I've forgotten the name of it. All right, it's not a very good name. And I think this galaxy deserves a lot better than what it's gotten. My supervisor might disagree. He's not, yeah. Anyway, guys, I want to present to you the cosmic bum. And I think it's honestly one of the most beautiful lenses in the whole world. I mean, Alessandro showed us a lot. I showed you the smiley face of the universe smiling at us. But what gravitational lensing has given us more than anything is the intrinsic bum of the universe. And I just want to leave you with one final quote from the book that I showed you earlier. And it's a quote from Sir Roger Francis Rectum, who was a professor at Melbourne University in Australia, 2002. And he wrote a book called The Origins of the Universe. And it goes, There are many theories about how the universe began, but the truth is most of the theories are just that, theories. All we know for certain is that in the beginning, there was a bum. Thank you, everyone, and you're welcome. I will take questions now.
Thank you very much, Kirsty, for this very entertaining talk about the intrinsic property of some component of our universe. That was very interesting, and we already have some questions.
Yeah.
The first one is, how long do these outflows last for? Do all galaxies have one at some point in their lifetime?
Ooh, yeah. So outflows like the ones we see in this galaxy, these really extreme outflows that are pushing out, like a quarter of the mass of the galaxy, these don't last for very long. So on that plot that I showed you at the beginning, I mean, for a galaxy, they probably last only sort of a certain, maybe like a few mega years, not even, because all of that gas gets pushed out very quick, and then the stars have nothing to form out of, and the galaxies sort of just die and go sort of quiescent and dead. But in saying that, galaxies have outflows the whole way through their life. Maybe they're not as strong as the ones that we see here, but where there is star formation or where there are black holes, there will always be outflows. Outflows don't necessarily have to be super powerful, and they don't necessarily have to push gas completely out of the galaxy. Sometimes the outflows just sort of pop and then they reaccrete back onto the galaxy. So they experience them the whole way through their life, but this phase is quite short in a galaxy, this sort of teenage phase. Yeah.
Thank you. And I think you already gave some hint, but still there is a question that what causes such strong outflows in galaxies?
Yeah, so in the case of this galaxy, it's really just the star formation. So when you have a lot of star formation occurring in a galaxy, so it's got a lot of gas and it's converting it into stars very quickly, you're forming all of your stars. Now, the biggest ones of those stars, they burn very bright and they burn very fast and they die very young. And these are the ones that go supernova. So at the time where you're forming a lot of stars, you have a lot of supernova and it's very, very tightly packed in the galaxy. And if you have all of these supernova going off at once, then sort of the pressure builds up in the galaxy and all of that combined energy sort of pushes the gas out of the galaxy. You can also have it from supermassive black holes. So like a big black hole in the center sort of accretes gas and dust onto it in stars and then shoots jets off in the opposite polar direction. So you can also get outflows from that. But yeah, it's just the combined energy of solar winds, supernova, black holes, radiation, all of that. It just sort of builds up and it pushes it out.
Mm-hmm. Thank you. And then we have another question. Why is the outflow only in neutral gas? Do you not expect molecular outflows?
Oh, yeah, that's an excellent question. Actually, we expect outflows in all phases, so not just neutral. I've chosen to look at the neutral gas here because, well, yes, okay, so we expect ionized, molecular, and neutral gas. We also expect dust in outflows. In terms of the mass in the outflow, generally the molecular or the neutral gas will dominate. So ionized gas is sort of only a little part of it, although the ionized gas is quite often the fastest part. So if we want to study the impact of the outflow on the galaxy, then we want to look at, for sure, either the molecular or the neutral gas. And that's why I've chosen to look at the neutral gas in this galaxy, because I want to look at the biggest component of it. But for sure, this is something that actually we really want to do with these galaxies, to observe all components of the outflow and then to get a combined idea of, what impact is that outflow having on the galaxy. So yeah, that's a very good point.
Thank you. Then we don't have a question, but there is a comment, and I personally feel that I should read it for you. It's
Okay.
from C. Butler. He said, well done, Kirsty. I wish you had explained your life's work as simply as that for me previously. So
Okay, so I should say congratulations for waking up at 2 a.m., Dad, and thanks for listening.
well, that's pretty sweet of him. Okay, so with that, we are at the end of our questions and sessions. So thank you, Kirsty, again, and thank you everyone for your questions. We now move on to the answers to our quizzes. Martha.
Whoop.
Thank you, Ramim, and thank you, Kirsty. That was a great talk. It was a great end to the day. We will now move on to the answers of the games. So for our first game, you had to guess whether the image we showed you was a gravitational lens or not. So the first one is indeed a gravitational lens, and so is the second one. Not the second one, the third one, sorry. The fourth one is a gravitational lens, and so is the fifth image we showed you. Number 6 is not a gravitational lens. Number 7 is not either, nor is number 8. Number 9 is not a gravitational lens either. And we finish with number 10, which is a gravitational lens. Now on to the second part of the game with our trivia about gravitational lenses. So if you were paying attention to Alessandro's talk, he mentioned that at some point that there have been about 1,000 gravitational lenses detected so far. So that was an easy one. Gravitational lensing does not change the color of the image of a galaxy. And it has shown us that most stars in the Milky Way have at least one orbiting planet around them. Number 4, what kind of lens is capable of producing images with the largest angular separation in the sky? That's a cluster of galaxies. Number 5, the first multiple image gravitational lens was discovered in 1979. And it was our sun, unsurprisingly, the object that acted as the lens in the first ever detection of bending of light by gravity. Number 7, what is causing such a time delay between images of a lens supernova is the light taking different paths with different distances. And for our last question, gravitational lensing has a strong effect on all of the above equally. All light rays are equally affected by gravitational lenses. And then for our tiebreaker question, the furthest gravitational lens ever found, the light from it took 9.4 billion years to travel to Earth. And that's it for our games. Now for the winners, we have 2 teams tied up in first place with 17 answers right. But that's what we have a tiebreaker question for. And so the winner with the highest score plus the tiebreaker is ENL. So congratulations. We will get in contact with you to get you your prize. And now on to Anik for the wrap up.
Thank you, Marta. Okay. So, yep, there we go. Okay, well, that brings us to the end of this evening. We hope you all enjoyed these amazing talks and the games. And if you can't get enough of Astronomy on Tap, then check out other Astronomies on Taps for more online events. Our next event will be the 27th of July, so we really hope to see you again then. And of course, a big thank you to our speakers. Normally we give you these glasses in the Burgt, but we will make sure that they'll make their way to you. And also a big thank you to the other members of our team of Astronomy on Tap, because only a few of us have been online here with you today. But of course, there's a big team making this happen. So thanks a lot for all. And thanks a lot for everybody watching. We really enjoyed it. And we hope to see you again next month.